Hey, welcome back to Math with Patrick and Quill. Today is April 11th, and we have problem number 101 from this Daily Epsilon calendars to solve today. And the answer is 11. Looks like we have this theta right here, which is between 0 and pi over 2, I'm assuming radians. And when we plug it into this equation, we get 60 over 61. And then finally, when we figure out what this theta is, we can plug it into the cotangent function and get 11, supposedly. All right, let's take a look at this first line. It says that theta is between 0 and pi over 2. Basically, this just tells me it's in the first quadrant, or it's in like the top right of the standard xy plane. If you work with radians as your degree measurement, it all kind of starts with the idea that a unit circle, or one whose radius is 1, will have a circumference of 2 pi. And then, depending on where you land on this circle, you're going to have some kind of angle measurement from the x-axis. So we have some obtuse angle right here. We could also have some acute angle, less than 90 degrees somewhere here. And ultimately, if you break apart that 2 pi, which goes all the way around the circle, you can get 1 pi, which goes halfway around the circle, or pi over 2, which goes straight up. So the angle pi over 2 is the same as 90 degrees. And then this initial condition of theta being between these two values just tells me that I'm somewhere in this first quadrant. Why not? Let me use the highlighter this time and highlight this first quadrant right here. Okay. The second part is going to be the meat of this problem. This is really the hard part here, I think. Trying to figure out how do we extract this value of theta from this equation. So I'll just rewrite it. Cosine to the power of 4 of theta minus sine to the power of 4. Oops, that doesn't look like a 4 anymore. Of theta is equal to 60 over 61. Now, trying to just solve this directly would be pretty tricky, and solving it with guess and check would probably be impossible because there's an infinite amount of numbers between 0 and pi over 2 that we'd have to check. So let's use something a little bit more wise. I see we have a difference of squares. It's another factoring scenario where I know I can factor this as cosine squared theta minus sine squared theta times cosine squared theta plus sine squared theta. And this is all still going to be equal to 60 over 61. And right in front of us are two trig identities. This one right over here is the classic Pythagorean identity. If, again, you kind of work in that unit circle whose radius is 1, that radius could even be somewhere here, say. And then you draw a right triangle that kind of corresponds with this angle here. Let's call that theta to match the problem today. Using that SOHCAHTOA idea, where sine of the angle is equal to the opposite side over the hypotenuse, well, if you're working in a unit circle, the hypotenuse is 1. So dividing by that 1 doesn't really do anything to the value. And so the opposite side right here is just the length of whatever sine theta is. This will spit out some number between 0 and 1. I guess it would be also negative if you were kind of below the x-axis here. But I'm just thinking in that first quadrant, we're going to get some vertical length here between 0 and 1. And then you can do the same thing for the horizontal length right around here, where cosine in SOHCAHTOA, you can remember that cosine of theta is the adjacent side divided by the hypotenuse. The hypotenuse, again, is still just 1. So cosine of theta tracks this horizontal distance the entire way around the unit circle. Now, if you remember your Pythagorean theorem, you can do a squared plus b squared equals c squared, and ultimately you figure out that this expression right here is always 1. Does not matter what value of theta you plug in, it's always going to get you the number 1. I don't have as good of an explanation as to what I'm doing for the other factor here. This is just something that I learned as a trig identity, as in I just kind of take it as a truth and I don't really question it. I know that cosine squared theta minus sine squared theta is cosine of 2 theta. This is something called a double angle identity, and there's a few different double angle identities for cosine, and then there's a lot of double angle identities for other trig functions like sine and tangent. But for today, I'm using this double angle identity for cosine, and it's just a pattern that I've recognized after working in trig enough. So it looks like cosine of 2 theta is equal to 60 over 61. Still, it's not clear. I simplified it a lot. I mean, my terms here had like to the power of 4, and all of a sudden I have something that looks a lot more simple. Yeah, let me see if I can kind of deconstruct this into a right triangle. Cosine, again, is going to be adjacent divided by hypotenuse. So I could draw a right triangle whose adjacent side is roughly the same length as the hypotenuse. We could have a 60 here and a 61 there. And cosine of 2 theta is going to be equal to 60 over 61. So this right here is going to be my angle 2 theta. I'm not really sure what theta is yet, but it's going to be in that triangle right there. And well, let's see if this is a right triangle. I could do the converse of the Pythagorean theorem. Essentially, actually that's not true. I'm assuming it is a right triangle. Never mind. Just the normal Pythagorean theorem. I just want to solve for this side right here. A squared plus b squared equals c squared. A squared plus 3,600 is equal to 3,721. In my head, I added 2 more 60s, and then I added a 1 to get to that number. And that means a squared is equal to 121. Oh, so it's a whole number. A is 11. Okay, so I have a right triangle, and this 11 just showed up, which is suspicious because it's today's date. But I'm not exactly sure how to get theta by itself. I had to look this one up. You know how I was saying there are other double angle identities? Well, there's one for cotangent as well. Cotangent of 2 theta is going to be cotangent squared theta minus 1 over 2 cotangent theta. And not sure why, I just looked it up. I haven't really used this one all too much, but I trust that the trig identities I find on the internet are true. And cotangent is the reciprocal trig function to tangent. So over here, if tangent of 2 theta, and I'm just looking at this triangle right here, tangent from SOHCAHTOA is opposite over adjacent, so that's going to be 11 over 60. I know that cotangent 2 theta is going to be the reciprocal, or just the flip of that number, so 60 over 11. So 60 over 11 is equal to this double angle identity on the right. I really, really hope I can get maybe cotangent theta on its own. That would be nice. So let me see. I'll do some cross multiplication here. How about? So I'll do 120 cotangent theta is equal to 11 cotangent squared theta minus 11. So I did these two multiplied over here, and then I also distributed the 11 across the two terms over here. This kind of feels like a quadratic equation to me, where cotangent of theta is my variable. It's kind of like 11x squared minus 120x minus 11. But instead of x, I have cotangent. So let me see if that's useful. 0 is equal to 11 cotangent squared theta minus 120 cotangent theta minus 11. And again, like I'm really hoping that I'm able to like isolate this cotangent theta, and I don't really see it yet. Like if this were like a 121, like maybe I'd factor out an 11, but I don't have a greatest common factor here. And honestly, factoring might be really tricky and unfun. Like, here, let me see for a sec. So, like, if I wanted to factor this with whole numbers, I could do something like this. Oh, actually, this might work. Where I have a negative and a negative. So I need to make, and this is a big negative. So what if I do this, right? Because if I do first times first, I get 11 cotangent theta squared. Then I'm getting, yeah, minus 121 plus the 1 minus the 11. Okay, so this actually does factor. That's really cool. Except this x should be cotangent theta. And then this x should also be another cotangent theta. All right, and this is still equal to 0. And looks like for today's problem, all I need to do is solve for cotangent of theta. This is enough, right? I don't actually need to know what this theta is. Looks like if I have a product and the product is equal to 0, surely one of those two factors is 0. And it could be either. So maybe 11 cotangent theta plus 1 is 0, or maybe cotangent theta minus 11 is 0. And our solution for the day comes from this factor on the right side. If this thing right here is 11, then I produce a 0, and I know that this is 0. So that's super cool. I can just say that cotangent of theta is 11, and using like a little bit of substitution, knowing that x is the same as cotangent theta. Well, that's actually kind of funny that I was calling it x right here all along, and I was like, no, I shouldn't call it x. I didn't realize that it was actually x for the problem today. X is 11 because I could just substitute it in right there. Cool. So we're all done. I just want to double check like why I'm allowed to throw out this solution, because it also looks like cotangent of theta could totally be negative 1 over 11. But whenever cotangent is negative, I know that I'm either in quadrant 2 or quadrant 4. So I wanted that to be the highlighter. I know that I'm either going to be here or here. And that's because this fraction is composed of the opposite length and the adjacent length of my triangles. And so one of the two needs to be pointing in a negative direction. Not both, because if I have a negative horizontal distance and a negative vertical distance, then I would have like two negatives and they cancel. And so it's only in quadrants 2 and 4 that cotangent is going to be negative. And then from the problem statement earlier today, we know that we are living in quadrant 1 and 1 only. So I found it. Cotangent of theta is 11, and it's only 11. And I actually don't even know what theta is, but I think that's okay. I was able to solve for cotangent of theta, and I know for certain that that's 11. So thanks for coming along. We're all done. I'll see you tomorrow. Bye.